So I've given you back some of your work. Please look it over. And I would like you to hand in your notes for the week, please. And where's Yumi? Yumi is not here. Regarding the web pages, I asked you to read and summarize page 23, but some of you read Phonetics 2, page 23. It should have been Phonetics 1, page 23, odd syllable types. So for those of you who read Phonetics 2, page 23, well, all the better for you. You've got some extra information that weren't quite up to, but it's certainly useful. But please go back, everybody, if you didn't do it, read web page 23 on Phonetics 1. Phonetics 1, page 23. Read it, include it in your notes for next Monday, okay? We're going to concentrate on getting through Chapter 8 because we have some new material to cover, and it's more technical than the previous edition, and we are now getting a little bit behind in our schedule. We're going to have to really try to get through Chapter 8 because there's a lot of rather technical material, which should not scare you, but we need to move along, and we'll need to really concentrate, to focus, to get through it and understand what's going on. So we're on page 187, and we're going to just start with the beginning of the chapter. Whose turn? Do we know whose turn it is? Who was the last person to read? Anybody remember? It doesn't matter. Let's just get started. Tina, you're starting.
Chapter 8, Acoustic Phonetics. We've looked at...
That was okay, except for you're saying acoustic. It should be acoustic. First of all, igen, irritabien. That's something you have to keep working on. And in this case, it's just a schwa, though. So acoustic, acoustic, 都可以, but let's just use a schwa. Acoustic phonetics. Acoustic phonetics. Everyone?
Acoustic phonetics.
Good.
Acoustic phonetics.
Good.
We've looked at a few spectrograms in earlier...
Special.
Spectrograms.
Spectrograms. Oh, I heard special. Spec, not spac. Spec. Yeah. Spectrograms.
In earlier chapter of this book.
In earlier what?
Chapters of this book.
Right.
This chapter is about...
This chapter.
This chapter is...
Not these. Once more. This chapter.
This chapter...
There we go.
...is about the acoustic properties of speech that we can see in spectrograms.
Spectrograms. Right.
Aiming to teach you how to read spectrograms.
You're still saying spectrograms. It's short, and you hardly open your mouth. Spectrograms. That's good. Yeah.
Spectrograms.
That's better.
Figure 8.1 shows us...
Figure, not figure.
Figure.
Right?
Figure 8...
You're still saying figure. There we go.
Figure 8.1 shows us spectrograms of a... Spectrogram.
You had an S there the first time.
Of a woman describing some of her experience.
Describe of a woman describing some of her experiences. So it doesn't go describing some. Some belongs to some of her experiences. So see which parts belong more with other parts and then divide them up accordingly.
A woman describing some of her experiences in politics. She says. She says.
Everyone, she says. Nobody says, okay? She says.
First campaign I worked in.
Campaign.
There
we go.
I worked in was for John Kennedy in 1960.
All right, a lot of you say 19, and it's 19, not 19. 19. Everyone, 19. We're going to listen to it in 1960. Let's listen to it. Oh, wait, why don't you read one more sentence so that we know what we're going to be listening to. Go ahead.
On the CD that accompanied this book.
That That what?
accompanies this book.
Book.
You can listen to this sentence as it was originally recorded and in two filtered versions.
Keep going.
In the high-pass version of the sentence, the top part of the spectrogram was allowed to pass and everything in the spectrogram below 2500 Hz was erased. Try looking at a
Try looking at a 是属于 spectrogram.
Try looking at a
我刚说 looking 后面断 because at belongs to at a spectrogram.
Try looking at a spectrogram
Right.
of the high-pass filter file in WaveSurfer, and comparing it to the spectrograms in figure
To the
spectrogram.
spectrogram. Gram.
Spectrogram
There.
in figure 8.1.
We'll point 那个 T 不要漏 Yeah. 8.1. Everyone? 8.1. Don't miss that stop. That point. It's not 8.1. It's not 8.1. 都不是. It's 8 point. Can you hear that long stop there? 8.1. Okay. We're going to listen to the first recording, which is just a normal recording of what she said. What was the sentence she said? Everybody read it together. Go ahead, go. Not 19, you're still doing it. 19. 你们还是有这个习惯. It's just about every Taiwanese has this 习惯 of 19, but it's 19. All right, I'll read it and you try it. First campaign I worked in was for John Kennedy in 1960. Go.
First campaign I worked in was for John Kennedy in 1960.
19. 19. Put it in your notes because just about everybody in Taiwan says 19 instead of 19. We need both of those N's. 19. We're going to listen to it as it was originally recorded.
First campaign I worked in was for John Kennedy in 1960.
Sounds pretty normal, right? But now we're going to do something with this recording. We're going to filter it. Remember we were talking about source and filter? And filter in Chinese literally is 过滤, right? We're going to 过滤. Now when we 过滤, that means we keep some things and we let some other things pass. 有一些东西把它过滤掉，有一些东西不要，有些东西会保留. In this case, in the first filtered version, we're going to allow the top part to pass. By here, when we say pass, that's what we hear. It's not what we're throwing away. We're going to allow the top part of the spectrogram to pass. That means that's the part that we will hear. But everything below, how many hertz? 2,500 is a little easier. 2,500 is correct. 2,500 hertz. Everything 2,500 hertz and below is going to be removed. It's going to be erased. We're not going to hear those frequencies at all. Now remember that our normal speaking fundamental frequency is about how much? She's female, right? How much? Anybody remember about? Yeah, about 235 for females. For men, it's maybe, depending on how deep your voice is, 120 to 180 maybe, depends on your voice. For females, it's somewhere around 235. So that's our fundamental frequency. Now, that's going to be gone. The G-pin is going to be gone. And we are going to also have a lot of the lower the lower formants are going to be gone as well. 所以有一些共鸣那些会不见了. Everything under 2,500 hertz is going to be erased. So let's hear what happens if all those frequencies are missing. And we call that high pass. That means the high frequencies are allowed to be recorded or to be heard. That was the same sentence. Listen again. Everything 250 hertz, 2,500 or 2,500 hertz and below is now gone. We're only hearing frequencies that are 2,500 hertz and above. Listen again carefully. All right, how would you describe that? How does it sound to your ears?
Like an alien.
Like an alien, okay? That's a pretty good description. Anything else?
Like crickets.
Crickets, okay, yeah. Like an alien, like crickets. Like crickets, they're both pretty good.
It sounds like like someone else is talking on the phone, but you cannot hear it very clearly.
That's another very good description because phones filter our speech. So all three of those were very good descriptions. They're all examples of high frequency sound that we encounter in our daily lives. So yes, it's like on a, sorry?
You said that it's a sound that we encounter in our daily life, but we don't encounter aliens.
Aliens on TV, movies.
Okay.
Otherwise, how would you know? Right? Obviously heard them. I was just writing about aliens yesterday. It was a 童书. So they were talking about aliens. We hear aliens all the time in 广告, right? TV shows, movies. Actually, otherwise, how would we know what an alien sounds like? We don't know. It's what we imagine. So in all kinds of presentations and all kinds of characterizations of aliens, that's what we hear. You know, we tend to give them a high-pitched kind of voice. All right, and if the phone connection is really, really bad, that's something like what it sounds like because we're only getting some high frequencies. But actually, those are not the frequencies we normally get in a phone connection. Those frequencies, most of those are cut off as well. But anyway, is it pleasant to listen to? No, it's not pleasant to listen to. Now, we don't have the spectrogram of the high-pass filtered file. We have the original spectrogram on the next page. If you look at 188, that's the original spectrogram. So find the 2500 mark on the left and just imagine everything below there is white. Just pretend that everything below there is white. That's what you just heard. We're going to go on now. I will just read this because it's just descriptions of what we're doing. So when you listen to the high-pass filtered version of this sentence, you may notice that it sounds very tinny. Tinny is a good adjective to have ready when you want to describe this kind of sound. Tinny means 很不响亮. It's 叽叽喳喳叽叽喳喳这种声音，那叫 tinny. It's sort of like striking an empty tin can. 一个空的罐头去敲一敲，敲一敲，差不多就是这个声音。The fricative noises are quite prominent. So you heard a lot of 叽叽喳喳叽叽喳喳. Those are fricative noises. They were quite prominent. And the intonation is pretty indecipherable. Indecipherable means that we can't interpret it easily. Cipher is a code. Decipher is 解码, to unlock the code and understand what the code is trying to say, or is trying to hide, actually. Indecipherable means you are unable to unlock what in the world it is. And in this case, it says we hear a lot of friction, a lot of fricative noises, but the intonation is largely hidden from our ears. We can't really tell. Instead of what was the sentence? First campaign I worked in was for John Kennedy in 1960. We can hear the intonation really clearly when it's not filtered. The fricative noises are quite prominent and the intonation is pretty indecipherable in the low-pass version. Now we're going to listen to another filtered version. In this version, we're going to let the lower frequencies stay. We're going to keep those, but we're going to cut off the higher frequencies. So the low-pass version keeps the bottom part of the spectrogram, and all of the sound energy above 1,000 hertz was erased. So these have overlap. No, actually there's a big piece that we're sort of missing in the middle. We didn't hear anything under 25 hertz the first time. The second time, we won't hear anything, what? Above, right. So we didn't hear anything below 2,500 hertz last time. We won't hear anything above 1,000 hertz this time. So there's this big gap that we're not covering. We're going to ignore that for now. I guess it's for to make it more dramatic. So this version of this sentence sounds more boomy. Boom, 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 boom. Now, I want you to predict what it's going to sound like in your mind. Just imagine, based on the original recording. Then on the filtered version that gave us only the higher frequencies that sounded tinny and we heard fricative noises. Now imagine what it will sound like if we only listen to the parts 1000 hertz and below. Just imagine in your head. Everybody listen in your head. Ready? Okay, that's what you imagined. Now let's see if it matches what we have here. Was it similar to what you imagined? No. Can you describe what you imagined? Probably what I tried to imitate, booming. How is it different, Amy?
It feels like hollow, like you're talking through a tree trunk or something.
Uh-huh, that's right. We hear sort of echoes, resonances. Anybody else, Vivian?
I think it's like a man talking very low pitch.
Okay, in a low pitch, that's right. It's all below 1000 hertz. Anybody else? Tina, any reactions?
I think it's like the chicken picking up, eating something.
Chicken's eating something. Oh, okay, there we go. Yeah, that's interesting. I love these animal comparisons. And that means you still know what animals sound like. I'm very happy to hear that. Okay, because a lot of people don't have much contact with animals these days. Okay, let's listen again. All right, that's the second filtered version, below 1000 hertz. What next? This version of the sentence sounds more boomy, instead of with prominent vowels and intonation. So we could hear the intonation better, the parts that were higher pitched and more stressed. And we could also hear a lot of vowel sounds because the vowels are all below 1000 hertz. Fricatives go above 1000 hertz. All the vowels are below 1000 hertz because they're voiced. So it's just a fundamental frequency. That's the most important part that we're hearing, plus the two formants, which go a little higher, but they can only, some of them only go as high as 2500 hertz. So for the vowels, we get more of them. Actually, we didn't get really clear vowels at that, but we got the sensation of vowels. Listening to filtered speech and looking at spectrograms of filtered speech can give you an appreciation of the information that is available in speech spectrograms. So this is an important part. Although I found this a little bit difficult as an introduction, with the background we have now, I think that you can appreciate what Professor Johnson was trying to do here. He wants you to know that this part of the spectrogram has this kinds of sounds, and this part of the spectrogram has these kinds of sounds. So now you have a pretty concrete idea of what parts of the spectrogram represent what kind of sounds. Okay? That's what he was trying to do. You can hear that speech has high frequency components and low frequency components. In fact, the sounds of language are distinguished largely by the detailed composition of energy in the vertical dimension of the spectrogram, the frequency spectrum. So if we want to learn about the details of human spoken language, we're mainly talking about different frequencies. Everybody understand what we said? So if we want to get the details of human speech, we're going to have to look at the different frequencies that are represented in human speech. That's the point he's trying to make. In this chapter, we will present the source filter theory of speech production and discuss many of the acoustic patterns that distinguish the sounds of language. Now, this was sort of heavy, but with our background, it should have been like a kind of a good introduction to the kind of information that we're going to be dealing with in this chapter when we're looking at spectrograms. Is it pretty clear? Are we okay? Good. Why don't we go on? And I may cut you off and take over myself for the longer paragraphs and because I need to demonstrate things. So how about our next reader after Tina?
Source filter theory.
Right.
In the first chapter of this book, we discuss.
This 需要那个有那种 contrastive stress 吗？
In the first chapter of this book, we discuss.
1 second. What would it mean if we said in the first chapter of this book? Yeah, that's right. Everybody get that in your head now. Whenever you stress something like that, you're contrasting it with something else. This book, it's different from that other book we were just reading. Remember that you're always giving information like this when you stress something. Okay?
In the first chapter of this book, we
All right.
we discussed how speech
Say it
sounds.
again.
We-
After book 后面.
Book.
Uh-huh.
We discussed
Okay.
how speech sounds can differ in speech,
Pitch.
in pitch, in loudness,
Not in loudness. In.
in
Not
loud,
in.
in loudness, and in quality.
Good. What points was I trying to make? Number 1, don't say peach 跟桃子没有关系. Pitch. And we have continuation rise that we use in lists, in pitch, in loudness, and in quality. In, make sure you're not saying ing. Ing is Taiwan English. In. Go on.
When discussing differences in quality,
Quality.
good.
Good.
We noted that the quality of the vowel
Of
a vowel
Right.
depends on its overtone structure.
on its.
Overtone structure.
That's better. Overtone structure.
Overtone structure.
Good.
Putting this another way. Putting this another way.
There we go. Link. Yeah, we don't say an other. We say another.
Another. We can say that a vowel sound.
We can say that. We can say that.
We can say that a vowel sound contains a number of different pitches. Different pitches
Good.
simultaneously.
Very good. You're going to have to stop and think for some of these because when you think, then you remember it and you get the right one. 它没有含有很多的桃子，它是同时不同的音高，不同的音高。Okay.
There is the pitch that at which it is actually spoken.
Which is what? The pitch at which it is actually spoken is the fundamental frequency. All right, we're going to have to be really comfortable with these ideas. We will soon because we're going to talk about them so much. The pitch at which something is actually spoken, we're talking about the rate of vibration of the vocal folds. That's the fundamental frequency. Okay?
And there are the various overtone pitches.
Overtone pitches.
Overtone pitches that give it its distinctive quality.
All right. That give it its distinctive quality. And here we are talking about vowels. Remember the demonstration we did last class? It's those overtones that give us the sensation of vowels. Different overtones from different sized and shaped tubes will give us different vowels. So they're talking about the formants here. The resonances in the vocal tract that we hear due to the size and shape of different cavities in our oral tract. Okay?
The overtones are called formants, and the lowest 3 formants distinguish vowels from each other.
And the lowest 3 formants distinguish vowels from each other.
And the lowest 3 formats distinguish vowels from each other.
Or distinguish vowels from each other. This time you could probably stress it because 我们就很强调这个母音和这个母音要听成不同的母音是因為 overtones 的关系跟它的那个 overtone structure 的关系，因为不同的 formants. Okay, keep going.
The lowest, format 1, which we can symbolize as F1, can be heard by tapping on your throat. If you open your mouth, make a glottal stop, and flick a finger against your neck just to the side and below the jaw. You will hear a note just as you would if you
Just as you would.
Right,
因为 if 是连接词，对不对？所以要听。
Just as you would if you tapped on a bottle. If you tilt,
Tilt 是斜着摆呀。
If you tilt your head slightly backward so that the skin of the neck
Backward 要重一点。
so that the skin of the neck is stretched while you tap,
Stretched.
while you tap, and you may be able to
没有 and.
you may be able to hear this sound somewhat better. Be careful to maintain a vowel position and not to raise the back of the tongue against the soft palate.
Soft.
Soft
Good.
palate. If you check a complete set of vowel
Complete your
positions,
T.
complete set of vowel positions,
Good.
E, I,
A.
O, U, U.
Good.
With this technique,
With this technique. Right. Everyone, technique. Now that's a French loan. IQUE, then you know it's from French.
you should hear the pitch of the first format going up for the first four vowels and
First
down.
four vowels.
First four vowels and down for the second four vowels.
For the
second
second four vowels.
four vowels.
Right, we've got repetition here. You should hear the pitch of the first formant going up for the first four vowels. 其实 vowels 我们已经知道了, so I stressed it, we don't need to stress it here. Going up for the first four vowels. If I say first four vowels, do you know what's coming? As soon as I say first four vowels, what's coming? Second four vowels. So that's one way that we make it easier for our listeners to understand us. We're already giving them a preview of what's coming. If they have the preview, that frees up their processing power to concentrate on other important things. Any repeated information, according to information theory, we can find ways to transmit it more efficiently. One way we transmit it more efficiently is we de-stress it. We don't 不要放重音，因为重音 takes more resources, 对不对？它比较耗费资源。So we take off the stress. And in this case, when we say the first four vowels, we already know that first and four are going to be contrasted. And what comes after first? Second, right. And then four, we've taken off. I said we stressed it, we didn't. Okay, so the first four vowels, since four vowels are both de-stressed, we know that that's going to be repeated. It's going to be second four vowels. They could change it, but then that's playing tricks with our mind. This is the normal way to do it, and this is how we make life easier and happier and more comfortable for our listeners. We should all do that, shouldn't we? Shouldn't we try to make it easier for our listener to understand us? Because if they get too frustrated, if you lead them astray, if you said, for example, the first four vowels, then what would they expect? Yeah, then they'd expect consonants. So you see how important that contrastive stress is and how important the repeated information non-stress is. All right, so you should hear the pitch of the first formant going up for the first four vowels and down. So up for the first four vowels, and what else is coming? Down. Down is the opposite of up for the second four vowels. And let's just listen again very quickly. We're going to use the flick your finger or the creaky formant to hear them. So let's just use the creak. It's a little easier to do. Right, you can do it yourself. Why don't we listen first and then you can do it again yourself. So we want to hear the first formant going up. It should go up. As our tongue goes down, F1 goes up. So can you hear it going up? Let's do it backwards and you should hear it going down. You can hear it going down, can't you? All right, let's try the last four. So it's, the last four are supposed to do what? They're supposed to go down, all right. Did it go down? Let's hear it go up. All right, you can try it yourself now. First four. Go ahead. Okay, try the second four. Going really low, isn't it? Very good, excellent. You can hear it, right? So far so good. The second formant, F2, goes down in pitch in the series of vowels. Oh, I should have kept the microphone maybe. We'll do that for comparison. So for the second series of vowels, because F2 is the formant that's really close to our lips, and for E, it's very, very small. That means it's going to have a very high pitch. For I, your tongue is making that front of your mouth formant bigger, so it's going to get lower. That's why we hear it going down. We did this last semester, but it's a good review. So here it's the whisper formant. Going lower. Let's listen to it go higher. You try. Go back up. There we go, pretty high. So that's F2. We didn't do the vowels in the back because they're not as tidy. And that's for one reason for this is because the back vowels tend to be what? They tend to be rounded. And rounding is largely expressed where? In formant 3. Very good. So he wants to tell you about formant 3, but he says, and he says that it adds to quality distinctions, but there's no easy way of making it more evident. So we don't have a handy way to perform it and hear it ourselves with a little demonstration. So he's just saying that F3 will add quality, but it's mainly involving rounding and and rhoticization. Okay. Next reader, please.
How do these formants arise? The answer is that the air in the vocal tract acts like the air in an organ pipe.
In an organ pipe?
In an organ pipe.
Good.
Or in a bottle. Sound travels from a noise-making source in voice sounds. This is the vocal fold vibration to the lips. Then, at the lips, most of the sound energy radiates away from the lips for a listener to hear, while some of the sound energy reflects...
Well, some of the sound energy. We've got a contrast between most and some, right?
Okay. While some of the sound energy reflects back into the vocal tract. The addition of the reflected... The addition of the reflected sound energy with the source energy tends to amplify energy at some frequencies.
Watch out for contrast.
At some frequencies.
那个母音，第一个母音。
frequencies.
Right, good.
And damp energy at others.
Right, so listen to that again. This is really important. We talked about it in class last time and previously, but especially last time. And this is getting to the core of what we're talking about in this whole chapter. And we're talking mainly about vowels because those are the purest examples of what we want to talk about. Namely, we've got a source, we've got a fundamental frequency with an infinite number of overtones, remember? 背音 above it. We have our fundamental frequency with an infinite number of overtones above it that are all multiples of the fundamental frequency, 乘以2乘以3乘以4. That's what's coming out at the source. And then when they go through the filter, certain of these spaces in our vocal tract are going to sort of amplify. It's not really amplify because it does not add energy. So that part is a little misleading in some books. They use it as a metaphor. It makes it more prominent to our ears. It damps other frequencies. So maybe we got rid of the 200 hertz frequency, but we made the 300 hertz frequency very 响亮. That's what a formant does. That's what he's saying here. Go ahead.
Depending on the length,
right,
and shape of the vocal tract.
All right, depending on how long the vocal tract is, how long it is, and 它的形状，它都有关系，都会影响到我们得到的那个声音，得到的那些背音的共振风。
The vocal folds are then a source of sound energy, and the vocal tract, due to the interaction of the reflected sound waves in it, is a frequency filter, altering the timbre. Timbre.
This is from French. You can see by the spelling. Timbre.
Timbre of the vocal fold sound. In phonetics, the timbre of a vowel is called the vowel quality.
That's right. In this case, we might say the vowel quality and break the rule because it is a compound and you read it absolutely correctly. But we might break the rule when we're reading it here because, Annie? That's right, because it's in bold, right? And bold means it's new and important. You have to pay attention to it. When we really want to emphasize something, we often break the rules of compound noun stress, and we will emphasize both just because they're important. So in that case, it's a pragmatic concern that overrules our usual rule. Pragmatic is 语用学。这里的语用是说，因为重要，听的人可能也属于资讯理论的一个原因，对不对？是因为是新鲜的又重要的。So we're going to stress it. So when you listen to TV, the radio, and other broadcasted sources, you will often find that they don't follow the rules of compound noun stress. Why is that? If you listen to the radio or any kind of broadcast on YouTube or a podcast or anything, you will find that they often break the rules, and then you're going to start wondering if your teacher was misleading you, right? 他讲的那一大堆其实都是骗人的。Because when you listen to broadcasts, they often break the rules. What is their reason? Mm-hmm. So what? Exactly, because if you're a broadcaster, and you read like this if you're a broadcaster on the radio, the same source filter mechanism is at work in many musical instruments, in the brass instruments, for example. If people read like that on the radio, what would happen? You get fired, yeah, because
It doesn't make audience pay attention.
absolutely, absolutely, puts them to sleep. And for that reason, broadcasters, newsreaders, etc., they have to be very high. Chinese high, 很 high, yeah. If they're not high and excited and energetic, they will lose our attention very, very quickly. And because they are so high, we don't use it in English like that. This is Chinese, okay? Because they are so high, because they are so enthusiastic and energetic when they read, they are going to add stresses where we originally would not put them. Put that in your notes. That's important because a lot of people don't know that. I'll give you an example of where I think it distorted a linguistic study. I read a whole book about compound noun stress. I read a whole book about it, and I wrote a review on it. 我就写了一篇书评 because I'm so interested in compound noun stress because so many people ignore it. So that's how I got interested in it, basically. My students were not doing it. They didn't know about it. It takes training. So I read this book, and then I wrote a review on this book for Linguist List. And, or something else. Anyway, it was a review. Maybe it was for language. But anyway, when I read this book, I saw that they took most of their corpus. What's a corpus? Corpus 跟尸体没有关系. Right, that's right. Miranda again? 语料库, that's right. Their collection of spoken English, where did they get it? From the radio. So what's going to happen? Is that going to be an accurate reflection of the way we use compound noun stress in conversation? No, it's going to be distorted. That issue was not even addressed in the whole book. And I should add that the book was not written by a native speaker of English. However, the speaker was a native speaker of German. So if this person, okay, this is going to be available worldwide. I don't know if the author is ever going to see this video. But if the author had really addressed the issue of distortion of compound noun stress in the media, I think he would have had to change his methodology that he used to write this book. Do you see what I'm saying? 懂意思吗? You have to be really, really careful where you get your sources. You can't say, well, this is spoken English, this is good enough. In addition, what's the advantage of a radio corpus? I've used a radio corpus myself for Chinese, but I chose it very carefully. Can you just say, well, it's spoken English, this is okay? Obviously not. You have to think about your source. And in this particular medium, if there's a specific style typical to that medium, that's going to change your results. That's going to be different, make your results different from what they'd be if you studied ordinary people speaking. So I myself also used a radio corpus for one of my papers. It was a paper on contraction in Mandarin, the 脚踏车那篇，对不对？计程车、脚踏车，马上来 right? Instead of 马上来，马上来。So I collected most of my material for that from the radio. Now, you'd think that's a bad source because in the radio, 咬文嚼字, they speak really clearly normally. But I got it from a call-in program, and it was a particular 主持人who is no longer doing this job, who spoke really naturally. In fact, her listeners would often praise the program. 她说我觉得那个聊天很自然，她就是直接讲了，她在评这个讲话的风格很自然。这是 listener， 不是学 linguistics 的，她就观察到了。I could give you a sample of it sometime if you want to hear it. But she spoke exactly, pretty much like what I hear in everyday life in Taiwan. So in that case, I thought it was suitable for what I used, and I collected a lot of examples like 脚踏车. That's the way she talked. It wasn't typical radio speech. So keep that in mind in the future. If you do any kind of corpus linguistics, any kind of research using a corpus, you have to evaluate your corpus very, very carefully and determine if it represents what you are trying to study. Okay? Now, in this case, we would probably say it's called the vowel quality. We'd slow down, make it really clear and explicit, and stress it, just because it's a new term that will probably be in a test, right? Okay, so anything in bold, you're probably going to be tested on it. If you're going to be tested on it, it's because it's important. So keep that in mind. We often break the rules when we really want to stress something important. I think we understood this. Did we understand this paragraph? How do formants arise? Is there anything I want you to read it over silently yourself, and I want you to tell me if there's anything that's not perfectly clear. If there's not, raise your hand and then we'll discuss it, okay? So read it over now to yourself. Look up when you're done. Vivian, clear? Or are you still working? Okay, go ahead. Miranda, you're done? Everything clear? Good. Look up when you're done. Okay, Bella, everything clear? Perfectly clear. Okay, Carol? All clear? Jerome? Any questions at all?
The questions are about words that I don't know, so I think I'll look them up in the dictionary.
Look up what?
The words I don't know.
Oh, just ask, and then we'll clear them up now.
Like damp and timbre.
Okay, you asked excellent questions. Those are key words that we're going to use. We mentioned them briefly before, but we didn't stress them. Remember when I said that we hear the fundamental frequency really clearly? And then due to the cavities in the vocal tract, we may hear 300赫和700赫可能会特别清楚。可是没有哪个空间是有200赫这样的一个自然的频率，可能没有。In that case, the 200 hertz overtone, are we going to hear it very clearly? No, because it's not being amplified through resonance. 因为它没有哪一个空间有200赫的共鸣，所以200赫的它就我们听不到，等于是被压抑了、压制了。That's what damping is. Damping is 我们吸收掉了，我们就听不清楚。That's damping， 就是让它变得就是很快就变得很钝，然后就没了。And then it decays. We call that decay. So that's damping of a wave. That means the time it takes for the wave to stop resonating. 那个响亮的那个声音就是停顿了，或者根本没有什么响亮。That's damping. Okay, that was an excellent question. Timbre means the particular quality of the vowel sound, which is created by the formants. 这些 formants 合起来，它营造的，它造成的这个母音，这是它的 timbre. The particular vowel quality is timbre, basically. The timbre of the vowel is its quality. So, anything else you noticed, Jerome? Okay, so those were the key words that we really need to pay attention to. Anybody else, even if it seems like a silly or very easy question, please ask. I'd like that to all be perfectly clear before we move on. Anybody have any tiny little question you want to ask? Even if it's a simple word that you can't remember right away. 都可以. Because I want this paragraph to be perfectly clear to you. He described the whole thing in one paragraph. Can you imagine trying to understand this paragraph if we had not looked at the web pages first? Would any of you have understood it? No, I don't think so. Even an experienced linguist, if they hadn't studied phonetics in great depth, they would have trouble with this paragraph. But now with your background, questions and probably further demonstrations, 都可以吗？都蛮清楚吗？那是很了不起. That means you've gotten over the biggest hump in acoustic phonetics. You understand the most important thing we need to get out of this whole chapter. We'll stop there. The bell has rung. Let's take a break. I brought 2 books for book sharing today. They are mentioned in this chapter. If you find you're really interested in this stuff and you want to get to the bottom of it, we will tell you the most important things, the basics, so that you'll know what's going on. But what, for example, Jerome was just asking about damping. If you want the details about how it works and how a wave behaves in a tube, and a wave behaves differently in a tube that's open or that's closed on one end, for example. It behaves differently. You will learn all about that in these 2 books. I read both of them. I wrote a review on this one. 网络上可以查到我这本书写的书评啊，网络找得到，就我的网站有放。And this is another excellent book by our other co-author. So this one is Elements of Acoustic Phonetics by Peter Ladefoged. This one's Acoustic and Auditory Phonetics by Keith Johnson. There's a newer edition out. This is the first edition. I don't know if there's a 3rd edition. I know there's definitely a 2nd edition. So, and this one is the 2nd edition of Ladefoged's book. I'll pass them around. If you are interested in this stuff, you need to, well, not you need to. It would be a good idea to work through one of these books. I would start with this one. This is pretty user-friendly. This one's a bit more difficult, but it's the same material. So if you finish this one will be easier to handle. There are many other books like it. There are actually lots and lots of books on this, basically on this same body of knowledge. But Ladefoged, I think, was a really, really great teacher. He's good at teaching. Not just that he knows this stuff well, but he knows how to present it so it's digestible. That's one of the really big things that Peter Ladefoged was very much admired for. So, passing these around for you to have a look at. Highly recommend them. If you don't want to buy them, I'm sure you can get them in the library. So that's book sharing. We're going to continue with what we were doing. Continue in the chapter, see how much we can cover today. So let's just keep going. If we are sure that we understand pretty much everything so far, is everybody up to speed on what we have already read in this chapter? We haven't gotten far, but that paragraph that I asked you to reread silently is a really key paragraph. So if you understand that, then the rest will be manageable. Let's go on.
The same source filter mechanism is at work in many musical instruments. In the brass instruments, for example, the noise source is the vibrating lips in the vibrating lips in the mouthpiece of the instrument, and the filter is provided by the long brass tube.
Okay, you're doing really well. Now you're not dropping so much. I think you mostly fixed it.
Because I use a high pitch to talk. It's not my normal talking pitch.
Uh-huh.
I
Raised your pitch?
raised my pitch.
It seems to help, but it's not just the higher pitch. It's that you're making continuation rises and you're not dropping. It's good. So let's understand what they're saying. They're using musical instruments as a comparison. And people who train people in voice for acting, for example, they often call your voice your instrument. They call that your instrument. 好像乐器一样. It means 工具, right? This was done with a certain instrument, 也是工具的意思, 也是乐器的意思. And they're going to use some comparisons now to musical instruments to help us better understand the human voice. They're talking, first of all, about the source here in brass instruments. For brass instruments, does anybody play a 小号, a trombone, or anything like it? Does anybody play a horn, any kind of a horn? No? All right. First of all, remember that when we were at the exploratorium last class, what did we use for our source in that experiment? A duck call. A duck call. And how did that duck call create vibration? Wendy just said it. Through a reed, right? 有个簧，槽子就是一个竹子头的一个黄色的簧。Through a reed. When you blow on it, it makes the reed vibrate, go up and down really fast. And I brought it this time. Here's the duck call. And this is available in Taiwan, imported from Indonesia, I believe. But you can look at the gozao when I pass it around. You can see that right here near the mouthpiece, they have inserted a reed that makes a buzzing noise, goes up and down when you blow into it. You don't have to do anything special, just blow. How many pitches will it produce? Well, basically just one pitch. It's not something that you can vary the pitch on like you can with a trumpet or with a trombone. You can vary the pitch up and down. But with this, it's just one pitch, and here's how it sounds. Okay, so that's the duck call. I'll pass it around for you to look at. It goes up and down. So you just have to blow. You don't do anything special with your lips. Brass instruments are different. Brass instruments, you have to vibrate your lips because they don't have a reed. Brass instruments don't have a reed. That means in order to make the air vibrate, you're going to have to make what we call a Brooklyn cheer. A Brooklyn cheer or a raspberry. You basically have to do that. That's how we create the vibration. We don't have a reed to do it for us, except for it will usually be at a higher pitch, so it'll be more like that, a little higher. Okay, not very melodic. Okay, and that's the vibrating lips in the mouthpiece, creating the vibration, that's the source. And the filter is provided by the long brass tube because the sound waves are going into the tube, and then the way they are reflected and the way they resonate in that tube is what creates the sounds that we hear. We vary our vibration of our lips according to the pitch we are trying to create. So for a very high pitch, our lips will be tighter or looser. They're going to be tighter, and for a lower pitch, our lips will be looser. So is a high pitch and is a lower pitch. Okay, go on.
You can verify for yourself that
Yourself, and also we never stress your, almost never stress your, for yourself. Yeah.
you can verify for yourself that the instrument changes the sound changes the sound produced by the lips by listening to the lip vibration.
Try it again. 断句.
You can verify for yourself that the instrument changes the sound changes the sound produced by the lips.
Changes the sound produced by the lips.
Changes the sound produced by the lips by listening to the
那然后后面那个 pause 久一点.
by the lips by listening to the lip vibration with the mouth
Lip vibration.
lip vibration with the mouthpiece alone. Make a circle with your index finger and thumb. With your index finger and thumb.
Index finger is right.
Index finger and thumb for simulated trombone mouthpiece.
Trombone, yeah.
Trombone mouthpiece.
Okay, simulated is 模拟. And so you can make a circle with your index finger and thumb, and it's pretty awful. But you can do that. It's better with a real mouthpiece, and then you can simulate the sounds that you produce in an instrument. And continue.
Similarly, in a marimba, the sound source is produced by striking one of the keys of the instrument, and the filter is provided by the tubes that are mounted underneath each key. One reason that the marimba is so much bulkier than a trombone is that it has a separate source filter system for each note in the scale. In a trombone, there is only one source, lips, and one filter, the tube of the instrument, and both are variable. The human voice.
Just remember that human behaves like an adjective. Okay?
The human voice is more like the trombone. Our vocal fold.
I think we don't use a schwa there. That's why I corrected you. Trombone.
Trombone.
Right.
The human voice is more like the trombone. Our vocal fold sound source.
Vocal fold sound source.
Our vocal fold sound source.
Fold beyond the D.
Our vocal fold sound source.
There we go.
Can be made to vibrate at different pitches and amplitudes, and our vocal tract filter can be made.
Vocal tract filter.
And our vocal tract filter can be made to enhance or damp different frequencies.
Slow down. These are important words. You need to slow down, or the listener will miss
And our
it.
vocal tract filter can be made to enhance
or damp.
different
There we
frequencies,
go. Yeah.
giving us the many different timbres that we hear as different vowels.
Okay, I'm just going to show you what a marimba is, because I'm guessing a lot of you probably don't know what a marimba is. Is that right? 很多人不知道 marimba 是什么. You've seen it before, but... Sorry? Oh, you played it before? Really? In a band or... Okay, there's a marimba. Doesn't it have a wonderful sound? It's very resonant. But if it only had these wooden keys, it would not be so resonant. Look at what it's got underneath the wooden keys. It's got pipes, and each pipe is tuned to the pitch that we want to hear. So the wooden keys are tuned, and the pipes are also tuned. And when we hit that particular pitch, what will the pipe do? It will resonate at that pitch we want, and then you can hear that that humming kind of sound from it because of its wonderful resonance. So that's a marimba and how it works. The source is the key when we strike it, but the sound is transmitted to each of the pipes, and then the pipe will resonate at its particular frequency, and that will amplify the sound that we originally produced on the key, right? So that's what they're talking about. This is a Zimbabwean instrument as well, and instead of pipes, in the Zimbabwean marimba, they use gourds. 他会用葫芦一样可以. So pipes is a more high-tech metal way of doing it. I wonder if we have... Let's try Zimbabwe if we can get one. Here they use pipes. Some marimbas use gourds. Okay, so I was wrong on this one. They are using pipes here too. They look like bamboo. So you can use pipes, but I've seen marimbas that also use gourds. That's another possibility. 可能是另外一个文化. Anyway, that's an example of source and filter. So, yeah? Which one? The first one? The third one? 怎样? Can you come and point? It looks like small hulu. I'm not really sure exactly what it is. In the jungle, it could be, yeah. The ones I've seen had bigger ones, but that could well be it. Thank you. Yeah, thanks for pointing that out. Turn that off for now. So anyway, all you need really is something with the same volume, somehow that produces the same resonances. And It doesn't really matter what you use, a pipe or a hulu or whatever it is, as long as its natural resonant frequency is that of the note that you want. Okay? I've got an instrument that you can practice on, that you can find out how it works on, and that is, I'll show it to you. It works like a trumpet, except for it's got a much lower pitch. Okay? Now, this is a modified didgeridoo. A didgeridoo is a native instrument of Australia. I've got a more authentic one at home. I didn't bring that because that one has invariable pitch. It's got a fixed length and you can't adjust it. But this one is retractable. 这个是不算改良，可是是有改变就是。So the way you play it is, does it have a reed? Is there a reed there? Can you see the light on the other end? You can see white on the other end, right? So there's no reed in there. So how are we going to get our pitch in an instrument like this? And the pitch is much lower. Now, I'm not at all practiced with trumpets, so that's why I had a hard time with the kinds of sounds. But for this one, it really is that low. And it's a little even easier if you make it long and you get a lower pitch. So. And then you can change the pitch. You'll have to change your rate of vibration. Okay? How about if you guys try it? I brought some alcohol wipes in a washcloth, so we'll wipe it clean. And if you have a cold, 现在正感冒, it's probably better for you not to. 如果算比较健康，我的是已经好了, so it should be okay. And I also have an alcohol wipe, and then I'll wipe it again. You can try it out. Let's see, Carol, why don't you hold it? Isn't that pretty? Well, if you're interested, I can tell you where in Taipei to get it. I waited many years to finally get one of these. And I just got it a few months ago. Yeah. And let's see if I can find the wipes. Who would like to try? First volunteer. All you have to go is, and you also have to make sure that your lips are sealed in the opening. You can't let air leak out of the side. Who would like to try? Okay, go ahead. Bella, come on. The lower one is easy. It's a very loose kind of a vibration. Okay, you can lean it on the floor or up here on the, whatever. You have to go and seal your lips in there. There. Yay! There you go. Okay, try a higher pitch. Okay, that's pretty good. That's pretty good resonance. All tired out already. You're not a wind instrument player yet, anyway. But if you think it's fun, you might want to try it out. Tina, you look kind of interested. Want to try? You can lean it on the floor. It's okay. Mm-hmm. Wow, good pitch. Make it shorter. You kind of have to experiment to get right at the pitch where it resonates the best, but that was pretty good. Try one more. Pretty good, pretty musical. Okay, thank you. Well done. Want to try one more before we put it away for now? If there's time after class, go ahead, Wendy. It's easier with a lower pitch. Okay. Mm-hmm. You just have to experiment until you get the resonance. You experiment until you get the resonance of that length. Yeah. There we go. Okay, the rest of you, if you want to play with it, there'll be a little time after class maybe. Okay. So that's a modified didgeridoo, didgeridoo. And if you want to find out about that, there's lots of stuff online. And it's used in some pop music now, the Australian didgeridoo. It's not terribly mainstream. It's not very easy to listen to really long, but it's definitely interesting. Okay, so we're going to continue. We've got a formula coming up that's scaring everybody. Go.
We said above that the filtering action of the vocal tract tends to amplify energy at some frequencies and damp energy at others, depending on the length and shape. Length.
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 Put a K in there. Length.
Length.
Put a K in there. I want to hear the K. Length. Length.
Length.
Yeah. Some native speakers do say length, though. I think it's better to say length because it's got an NG. Go.
Depending on the length and shape of the vocal tract.
Good.
The length factor is pretty easy to describe when the shape of the vocal tract is simple. For example, if the vocal tract is shaped like a garden hose.
A garden hose.
A garden hose, exactly the same
Good.
diameter from glottis to lips.
To lips.
To lips.
Not leaps.
Lips. Its resonant frequencies can be defined by a simple formula.
Okay, he's going to describe what's in this formula below, so don't panic. He's going to describe in the next paragraph what we're doing. But I will tell you, first of all, that C is the speed of sound. The factor C there is the speed of sound. And he doesn't give us an exact number. The speed of sound is actually 340.29 meters per second. If it's at sea level, and if the air is dry, at 20 degrees Celsius or 68 degrees Fahrenheit. So you have to give all those factors before we can know the speed of sound. Why? Why do we need to know that it's at sea level, that the air is dry, and what the temperature is? Why do we need to know those things? If it's much higher than sea level, what's probably going to happen? Will sound probably travel faster or slower? Because resistance. Right. 阻力没有那么大 because the air is thinner as we go up. 比较稀薄. The higher we go, the thinner the air. So sound is going to travel faster. And also the temperature makes a difference. It's going to travel faster in warmer air or cooler air. Right. And also it's going to travel faster in dry air or in more humid air. In drier air. So all of those factors make a difference. And none of these apply to Taiwan, right? We're not quite at sea level. We're a bit higher, although not that high. And it's very, very humid here. It's usually like 80% relative humidity or higher. So there are quite a few differences. So what Professor Johnson did here is he picked an even number that's easy to calculate with. He picked 35,000 centimeters. Because it's 350 meters per second, then we multiply it by 100 to get centimeters, right? So everybody knows now where we got C. We're counting, we're calculating here with the speed of sound. And he rounded it up to 300, so it's 350 meters per second or 35,000 centimeters per second. The other two factors, the left one is pretty easy to understand. The one below, I cannot explain in this class because you have to read one of those books I just passed around to really understand it. But I can tell you, 它根据什么来算的. Let's go to the next paragraph and then I'll try to tell you what I know to make it clear. Go.
This formula says that resonant.
This formula is what?
This formula says that resonant frequency.
Slow down.
This formula says that resonant frequency number n, where n equals 1, 2, 3 for formants F1, F2, and F3, is equal to 1 subtracted from 2 times n.
All right, let's stop there. We're going to understand every single term. It's not going to be hard. First of all, the part on the left-hand side we now know is very easy. We're only going to have 3 to think about today, namely F1 or F2 or F3. So Fn is either 1, 2, or 3. And we'll do them separately. Then the next term is on the top, on the top part of this fraction here. So it's 2n. We multiply, for example, if it's f1, we multiply f1 1 by 2, which is 2, and we subtract 1, so we get 1. So we don't have to worry about it for the first format. We're just going to have the speed of sound, right? It's because 1 times c. So it's going to be 1 times 35,000. And then, so we're clear so far what we're doing. The reason we do this part in parentheses is why? Because we only want odd numbers. That's what it does, is it gives us odd numbers. Multiply by 2 and subtract 1. The reason is because we want an odd number. Why do we want an odd number? Because our vocal tract is a closed tube. 有一边是被封闭的话, it can only produce odd resonances. So 只有那个基数 the resonance 我们才听得到. So we have to get it odd. We have to make it odd. That's why. So we're only going to hear resonances with odd numbers. Okay, so now we're all clear on everything except 4L. Is that right? 都可以吗? So we want an odd number that's related to the formant here. We only want the odd number resonances. That's why we have to multiply by 2 and subtract 1. Multiplied by the speed of sound. Let's go on.
Multiplied by the speed of sound c, divided by 4 times the length of the vowel tract L.
Of the...
A vocal tract L.
All right, now we know what L is. L is length of the vocal tract. We need to know the length of the tube. You can see by the length of the tube it varies the pitch, right? So we know that length is important. And we're going to multiply it by 4. Now that's the part I don't have time to explain, but it's because of the behavior of a sound wave in a tube that's closed on one end. Just believe me for now. If you want the details, you can go online and look into it, explain it very clearly. So look into tube resonances. If you want to look it up, just go to Wikipedia, look up tube resonances, and it will explain it. Okay? And if you really, really want to, we could do it in class sometime, but it's not really that important for what we're doing. Long as you understand, because of the way a sound wave behaves in a tube that's closed on one end. I can tell you one thing. If the tube is open, the sound wave will end on a node. Do you remember what a node is?
The part that does not.
It's smack in the middle where it doesn't move, it doesn't vibrate, right? It's right in the point where the two sine waves intersect. So they're not doing anything here, right? That's the node. But then as the sine waves continue, there's this part in the middle where they're the furthest apart that they will be, right? That's called the antinode. 它距离最长的那个是它的 antinode. All right. So, with an open tube, it's going to just end on a node. But with a closed end, it's going to end on an antinode. So that means it changes how the wave behaves. And I can tell you one more thing that might be useful. If the tube is open, it gives you one pitch. If you close one end, you will get a pitch that is 1 octave lower. 就把一边封起来，你得到的音是后面开放的那个音的什么？低8度音。If you close one end, you get a pitch that's 1 octave lower. And that's also because of how sound waves behave in a tube that's open or closed. Are we clear so far? That's as much as I think we need to know of the actual physics of what we're doing on this. Let's go on.
For example, Peter Ladefoged's vocal tract was 17.
Vocal tract. Remember to pause after the subject.
Vocal tract was 17.5.
17.
17.
It sounds like you say 70 if you don't stress it. If you 17 point, so 17.
17.5 centimeter long.
Centimeters
long.
Right.
So the C divided by 4L part.
4 times the length. Yeah.
4 times the length part of the formula for his formant frequencies is 35,000 divided by 4 times 17.5.
All right, I brought a calculator just so you can see how it really works. Who is the most nervous about math? 就对数学有点恐惧感、有点紧张的人，请勇敢举手。Good, you do it. Now, Remember that the 2 times n minus 1 turned out to be 1, so it's 1 times c. c is 35,000. So Yumi, okay on that? 都可以吗? 35,000 is just the speed of sound that we're using for this, just for this exercise. So what we want is, first of all, 4 times the length of Peter Lattifogo's vocal tract, which is 4 times 17.5, right? How much is that? It's 70, right? All right, start over. Now take just this one. Start over. Now take 35,000 and divide it by how much? 70, and what do you get? 50 ma? Try it again. Input 35,000, 3万5. Yeah? Divided by? There we go. It worked? It worked, right? Okay, you can set the calculator aside for a minute. We know that it works. 他们不在乎我们. So if you trust Yumi, right, then you know that it works. So it's the speed of sound divided by 4 times the length of the tube. And we got 500. That's about the area of the first formant. We've just calculated our first formant. Now, if we want to calculate the second formant, who else is a little bit nervous about math? Who does not want to admit it? Okay, somebody else? Wendy, you want to do it? You're fine with math, though. You're fine with math. Okay, so start over. Let's read, and then we'll follow the instructions.
The constant c is the speed of sound and tells us how quickly a sound wave travels from the lips to the glottis as it bounces around inside the mouth.
Okay, absorb that sentence a minute. The constant, 这是一个固定的一个数字. We're just using it. It's going to change depending on many factors, but for convenience, we're using 35,000 centimeters. That's the speed of sound. And it's telling us how fast the sound wave goes from the lips to the glottis when it's bouncing around inside the mouth. Keep going.
The first term in a formula, 2n minus 1, defines a sequence of multipliers for this basic frequency value. So, Peter's first resonant frequency.
Okay, let's make sure we understood that. The first term in the formula, that's a sequence of multipliers. 就是, what's a multiplier? Something that we multiply a number by. What do you call that in Chinese? Okay, the thing that we multiply a number by, we just want to make sure that it is odd. All right, go on.
So Peter's first resonant frequency, the F1, was 500.
I would say the F1.
The F1 was 500 times 1 equals 500 hertz. The second ferment, F2, was 500 times 3 equals 1,500 hertz.
Or 1,500 hertz. So let's do that one. So to get the second formant, we have 2 times what? 2 minus equals 3 times? 3 times 35,000 is how much? All right, and we want to divide it by? You still remember? 70. Divided by 70. What do we get? What did you get? Or otherwise known as 1,500. Let's just say 1,500. I think I'm more used to it. Most people would probably use that instead. So we got 1,500. One more person to calculate the third formant. Who would like to? Grab. Miranda. Okay, clear it off. Now, that's the second formant, and we have one more formant to calculate. So F3, what do we do? 2 times 3 is minus is times 35,000. All right, so do that, Miranda. 35,000 divided by 70 equals? There we go, it works. So I just want to make sure that nobody thinks that this is scary and you're going to jump over it and ignore it, because you don't have to ignore it because it's really simple. So we have now calculated the first 3 formants. It's actually of a schwa. 其实是一个schwa的那个3个 formants. That's important to know because 它的那个分配比较均匀. Okay? So this paragraph is okay, right? All right, and that is about as math as we're going to get. We have a little more, but now it'll be even easier. Let's go on.
Different vocal tracts have different resonant frequencies. For example, Keith Johnson's vocal tract is about 16 centimeters long.
Centimeters
long. So his formants will all be a little higher.
All right, let's stop there. What is our dividend here? We're going to need what? Since his vocal tract is a little bit shorter, it's 16 centimeters, Miranda, times what? Times 4, and we get? 64. All right, everybody remember 64. We're going to use that. So F1 is going to be? 35,000 divided by 64, which is? 47. Pass it to Jerome. Can you please calculate the formant 2, second formant? That one is what? So we're going to use 3. We could just directly multiply by 3 because formant 1 times 3. That's another way to do it. But it's good to go through the formula so you know what's happening.
1,640.625.
Okay, so it's 1641. We round it up. We round it off. Okay? And then third formant, give it to Amy. So we have 5 times 35,000 divided by 64. What do you get?
2,734.375.
And so it's below 5, so we're going to just drop the part to the right of the decimal. We could get 2734. It comes out, right? So for me, I have an 安全感. When I figure it out, it matches what it says in the book. I think, ah, 松一口气. I'm thinking you might feel the same way. So we're okay now. We just figured out 2 sets of 3 formants each. One for Peter Ladefoged, one for Professor Johnson, okay? Let's keep going.
The length of the resonating portion of the vocal tract also differs substantially for different speech sounds. In vowels, the whole vocal tract, from glottis to lips, serves as the acoustic filter for the noise generated. The acoustic filter for the noise generated by the vibrating vocal folds. In fricatives, the resonating portion of the vocal tract is shorter. For example, in s, the portion of the vocal tract that serves as the acoustic filter. The acoustic filter is from the alveolar ridge to the lips.
You're doing the same thing as, you know, we don't have any contrast with ridge and filter. So if we say acoustic filter, we're implying a contrast. But do we have any other kind of filter that we've been talking about? No, so an acoustic is a noun or an adjective? It's an adjective, therefore is it a compound? No, so we still, even though we're using this word a lot, 它就是不够来让它成为一个 compound 或者有 compound stress. For example, vocal cords or vocal folds, we use that so much that has already taken on compound stress, right? But this one is not. Acoustic filter, 它就是 acoustic filter because 我们没有别的东西跟它做对比. And alveolar ridge is another thing that we use all the time, that we refer to all the time. But we don't say alveolar ridge because there's no other kind of ridge. There's only alveolar ridge. So we say alveolar ridge. So acoustic filter. Everyone, acoustic filter.
Acoustic filter.
Alveolar ridge.
Alveolar ridge.
Now watch those two because we're going to use them a lot, but they don't have compound stress. They're just regular phrases. So can you do that again, for example?
For example, in s, the portion of the vocal tract that serves as the acoustic filter is from the alveolar ridge to the lips.
You got it. Do we understand so far? The length of the resonating portion of the vocal tract also differs substantially for different speech sounds. So depending on the sound, we're going to have different lengths that we have to use to calculate. For vowels, the whole vocal tract, from the glottis all the way up to the lips, is like one acoustic filter for the noise generated by vibrating vocal folds. So when we're figuring out formants, vowels are the easiest things to work with because we've got this tube here. It's got different shapes and sizes on the way, but it's the easiest to work with. With fricatives, the resonating portion of the vocal tract is shorter. 会有共鸣的部分是比较短的. For example, in S, the portion of the vocal tract that serves as the acoustic filter is from the alveolar ridge to the lips. That's very, very short. 从你的齿龈到嘴唇，那距离是不是很短? So that means the pitches are going to be very high. That's right. Go on.
Thus, the lowest formant is with a vocal tract length of only 2 or 3 centimeters.
Centimeters. And length. Everyone put a K in there. Length. Length. Not len. Length. There we go.
Length of only 2 or 3 centimeters will have a much higher frequency than the form F1 found in vowels.
So for vowels, we're going from the glottis all the way to the lips. That's pretty long. For these fricatives, in addition, is not voiced. We still get resonances when it's not voiced, but they're much quieter. In any case, it's very, very short, so the pitches are going to be very, very high. Fricatives go way up there. And we're not going to get a fundamental frequency. That's going to be exciting those frequencies in the same way. Let's go on.
This explains why the fricative noises were so noticeable in the high-pass filtered version of the utterance in figure 8.1.
Do you want to hear it again? Let's just listen to it again. That filtered version that only gives us frequencies over what? Over how many hertz? Over 2,500.
First campaign I worked in was for John
Oops,
Kennedy
sorry,
in
that was the first one.
1960.
Let's go to the second one. Those are the frequencies we're getting with fricatives. We got some voicing there though because she had vowels and things. With it's just very, very fricative and buzzy. Okay, not so much buzzy. It's just singing. Let's go on.
The only fricative that does not have higher resonant frequencies.
Frequencies. Let's try this one, everybody. Listen carefully. Use the echo. Frequencies. Go. Frequencies. Good.
The only fricative that does not have higher resonant frequencies. Frequencies.
There we go. Sees. Try it again.
Frequencies.
There. Sees. Once more.
Frequencies.
It's getting better. Okay.
Then those found in vowels in the glottal fricative in the whole vocal tract from glottis to lips is involved.
Depending on what comes after it, though, of course. So for that's the only one that will not have higher frequencies because we're starting from way down here. Okay? We're okay? Let's go.
In addition to the length of the vocal tract, the frequencies of the resonant overtones, the formants.
Everyone, formants. Good.
Are determined by the shape of the vocal tract.
By the shape of the vocal tract. We've got a really high contrastive stress here. By the shape of the vocal tract. Not only the length is important, but also the shape, okay?
By the shape of the vocal tract.
Good.
We've been assuming so far with the formula.
So far, pause. With 介系词, we need to pause.
We've been assuming so far with the formula Fn equals to 2n's minus 1.
2 times n minus 1.
Or 2 times n minus 1 times c divided by 4L's.
4 times L.
4
right?
times L. That the vocal tract has uniform diameters. Diameters.
没有 S.
Diameter. As if it were a section of pipe.
Of pipe, right. I would say has a uniform diameter. It's not really wrong, but I would definitely put in other. Has a uniform diameter. 你把它当不可数也可以, but I would prefer an other. So, the vocal fold is not the same size. It doesn't have the same diameter at every point. 某些地方比较粗，某些比较细. Okay?
This is obviously an incorrect assumption for most speech sounds. For example, in nasal consonants, we have numerous side cavities branching off of the main passageway from from the main passageway from glottis to nose. The sinus cavities as well as the mouth cavity. Similarly, in lateral
Say it again.
sounds,
We have. Say it again. That part.
we have numerous side cavities branching off the main passage from glottis to nose. The sinus cavities as well as sinus. Okay. The sinus cavity as well as the mouth cavity. Similarly,
What is sinus, by the way?
I guess it's the passage from the...
Just tell me in Chinese. That's the problem. Don't use English to cover up when you don't know something. Just ask, what is sinus in Chinese? You often see it in these 诊所. Huh? What do you call it? 鼻窦. 鼻窦不是有鼻窦炎吗? You have inflamed sinuses. 鼻窦 is the sinus, the sinuses. Yeah, okay. Okay.
Similarly, in lateral sounds, the shape of the vocal tract is complex. Rather than go into detail for many different speech sounds, we will limit our focus here to vowel sounds.
Okay, that makes things a lot easier. And if you understand how vowels work, then everything else works pretty much the same. It's just got a few other things happening. Okay?
For a more detailed account for a more detailed account of vowel acoustics and the acoustics of the acoustic of other speech sounds.
Again.
Sorry. And the acoustics of other speech sounds.
Other speech sounds.
See Peter Lackford's book, Elements of Acoustic Phonetics.
Okay. Yeah. Or 不要那么快. Anyway, we should leave a pause there. Elements, not elements. Elements. Elements 是营养品. Elements. Alimentary. Canal. 是那食道. Okay? So elements. Can I have the book, please? Where is it? The Lattifogo book? And the other one. Thank you. So we'll just show it so we can show it more clearly on the video. So read that again. See what?
See Peter Lackford's book, Elements of Acoustic Phonetics.
Pause. Go ahead.
Or Keith Johnson's book, Acoustic and Auditory Phonetics.
Acoustic and auditory phonetics. We'd probably de-stress phonetics there because we repeated it. It's this one. And it's going to be a newer edition. This is an older edition. Okay?
The acoustics of vowels can be described in two ways. With tube models and
Pause. With tube models. We've been using a tube model, and we tried a tube just now. That's one way we can understand how resonances work in the human vocal tract, is by using tubes as a model, an idealized model of how things work. And
with perturbation theory.
Good.
Both of these descriptions are useful, yet overly simple descriptions.
Very good.
They're discussed in the next two sessions.
That was a nice place to break off. So Vivian starts next time, and you start with tube models on page 190. Do we understand just about everything? If there's some tiny things you don't understand, for example, where the 4L comes from, that's no big deal. But everything else, are we all sort of up to speed? Are we all in agreement? Are we all up to the point that we are in the book? Everybody understands? 有没有不太清楚的地方? All right, for Wednesday, please reread what we read today. Read it again. Read it out loud to make sure you get the intonation right. Make sure you understand every bit of the content. And then read ahead a bit so that it won't be such a big deal. At one point, he goes back to the original edition. It's the stuff that Ladderfolk had in his original edition. The new material 就是这个部分到 acoustic analysis 为止，那是新的, just so you know. And after that, we're going to be looking very closely at the mechanics of formants using vowels. Okay? And we need to move fast, so anything that you do ahead of time, any extra work you do is really going to help the whole class. Okay? That's it. We'll see you on Wednesday.